Okay, so welcome back to the next class. So in this class, we'll talk a bit more about the Galton-Watson process. Which is a probabilistic model for coronavirus spread. So the main theorem that we proved last time is theorem if X is the distribution of people infected by a single patient, then the probability of extinction is equal to eta star, such that eta star is the smallest non-negative solution to g of x of eta equals to eta. And g of x is the expectation of s to the x. Okay, and this is the generating function. So today what we're going to be looking at is a bit more about examples. So one of the things that we didn't say, and this comes from the modeling perspective, is what is the distribution of x? Okay, so this depends on your modeling. So let's start with like what happens if we take x in particular ways, so that we actually can see what is happening with the Galton-Watson process. Okay, so let's consider, for example, let's take x such that the probability that x is equal to 0 is equal to 1 minus p, and the probability that x is equal to 2 is going to be equal to p. Okay, so this is x is distributed as 2 times a Bernoulli variable with parameter p. Okay, so if we take x to be a Bernoulli variable with parameter 1, okay, so what is the expectation of x? The expectation of x is going to be equal, again, the sum over k equals to 0 up to infinity, times the probability that x is equal to k. So in this case, it's going to be 0 times 1 minus p plus 2 times p. Okay, so this is 2 times p, and this is what we were calling R0. So if p is less or equal than a half, then from last class, the probability of extinction is equal to 1. So here, if we know that the expectation is less than 1, then we know that each person has the probability of infecting less than one person, so the generations of infected people are going to become smaller and smaller, and so eventually they are going to actually become extinct. So now, but if p is bigger than a half, we can still find the probability of extinction explicitly. Okay, and what we are going to see is actually that this differentiation between p less than half and p bigger than a half is just anecdotic if we actually look at the theorem that we are going to look at the probability of extinction is the least, is the smallest solution to g of x eta equals to eta. So the question is, what is gx of s? So in this case, g of x is the expectation of s to the x, which is the sum from k equals to 0 up to infinity of s to the k, the probability that x is equal to k. But again, this is just going to be 1 minus p plus s squared times p. So if we want to find solutions to gx of s is equal to s, what we need to find is find the roots of p times s squared plus 1 minus p is equal to s. Okay, so we can pass the s to the other side and then get this is ps squared minus s plus 1 minus p is equal to 0. Okay, so let's try to complete the square. Okay, so how do we solve this? We can use the formula. I think in general it's good that if you understand how to complete squares. So complete the square. So here, this is the square root of p times s squared. And then this term here, so if we put this minus a number a squared, this is going to be p s squared minus 2 square root of p times a times s plus a squared. So the way to complete the square is to choose a such that 2 times square root of p a is equal to 1. So then we take a to be equal to 1 over 2 square root of p. So here what we get is that this is square root of p times s minus 1 over 2 square root of p squared plus, so if we have a plus a squared, we have to subtract minus a squared minus 1 over 4p plus 1 minus p is equal to 0. So I hope I don't actually mess this one up. So this would be square root of p. So here I can take square root of p out as, or I can take, yeah, I'll just take p out as a denominator. How do I want to take this? So let's take, this is 1 over p of p times s minus 1/2 squared is equal to 1 over 4p plus p minus 1. So we multiply out by p, and so this gets multiplied by p. And so then what we get is that ps is equal to the square root of. And so here what I get is p squared minus 1 plus 1/4. Hope I'm getting this right. Okay, so this is p minus 1 minus 1/2. So let's try to get this thing here in this side is p squared minus p plus 1/4, which is just exactly equal. This is ps minus 1/2 squared. This thing here is exactly p minus 1/2 squared. And so then what we get is that p times s minus 1/2 squared is equal to p minus 1/2 squared. So then here we have the positive and the negative. So we get ps minus 1/2 is equal to p minus 1/2, which implies s equals to 1, or ps minus 1/2 is equal to 1/2 minus p. So here we would get s is equal to 1 minus p over p. Okay, so then the solutions to gx of s, gx of eta equals to eta are eta equals to 1 or 1 minus p over p. So eta star is going to be the minimum between 1, so the eta star, which is the probability of extinction, is going to be the minimum between 1 and 1 over p. So here we can see that there is a transition, there is a change, transition, if p is bigger or equal than 1/2, or p is less than 1/2. So if p is bigger or equal than 1/2, then eta star is equal to 1. If p is less than 1/2, this is the other way around. If p is less or equal than 1/2, then eta star is equal to 1. And if p is bigger than 1/2, then eta star is equal to 1 minus p over p. So in particular, what happens, for instance, if we take p equals to 2/3, we are going to get 1/3 over 2/3. So then eta star is equal to 1/2. So in this specific example, if we take p equals to 2/3, then the probability of extinction is still 1/2. So similarly, we can look. So we can look at what happens if instead of taking. So we can see what happens. We can change the distribution x such that x is distributed like, let's say, 3 Bernoulli variable p. So what does it mean is that the probability that x is equal to 0 is equal to 1 minus p, and the probability that x is equal to 3 is equal to p. So in this case, if we look at the generating function of x at s, is just going to be, again, the expectation of s to the x, which in this case is 1 minus p plus p s cubed. So if we need to find solutions to gx of s is equal to s, then what we're going to get is that we need to find roots of ps cubed minus s plus 1 minus p is equal to 0. So, okay, so one of the things that we should realize, okay, so finding the roots of a cubic polynomial is a bit harder. So the way that one can realize how to do these things is to take, so we know s equals to 1 is a root. So what we can actually try to do is decompose ps cubed minus s plus 1 minus p is equal to s minus 1. And now we need to divide this polynomial by s minus 1. So in particular, the leading order term here has to be p times s squared. So, but then I'm going to get another term that looks like minus 1 times p of s squared. So then I need to get a term that cancels out with this term, which would be plus p times s. But then I would get a term that is p times s. So we're going to get a term that is like p times s. But if I have to have a term that is p times minus p times s, if I want to get minus 1 here, I need to subtract minus 1 minus p. Okay, so this is dividing polynomials. Okay, so I'm not going to bore you with like how to find the roots of this guy again. So then we have s is equal to 1 is a solution, or s is equal to minus p plus minus the square root of p squared plus 4p times 1 minus p over 2p. This is, or the other way around. So okay, so in a sense we get here minus a half plus or minus the square root of 1 plus 4 times 1 minus p over p divided by 2. So again, before we can actually look at the expectation of x, so the expectation of x is just going to be equal to 3p. Okay, so now what we realize is, as I said before, if the expectation, this is R0. If R0 is less than 1, we expect that the only solution, the probability, the smallest solution is going to be s equals to 1. But if R0 is bigger than 1, so if 3 times p is bigger than 1, then you expect that there is a smaller solution. So if we actually look at this, the positive solutions of this thing, so if we take the minus solution here, we get something negative. So then if p is smaller than a third, smaller or equal than a third, then eta star, which is the probability of extinction, is equal to 1. And if not, if P is bigger than a third, then eta star is equal to minus a half plus the square root of a half plus 4, 1 plus 4 times 1 minus P over P. Okay, so depending, so the point is that if you take P equals to 1/3 in this expression, you actually get exactly eta star. You get equals to 1. Okay, that's when the roots are all in the same place. Okay, so this is just to give you an idea of how you can calculate these things explicitly for these types of things. And then another thing we can see by knowing the distribution of x explicitly is we can actually calculate what is the probability that the virus has gone extinct after n generations. So after n generations, this is just Gn of 0 is the probability that Zn is equal to 0, which again, this is just Gx of Gx of Gx of Gx of 0. This is n times. Okay, so then if we take x to be distributed like 2 times the Bernoulli variable with parameter p, then p of z1 equals to 0 is going to be gx of 0, which is just 1 minus p, which is the probability that the first person doesn't infect anybody else. So the probability that the first person doesn't infect nobody else is 1 minus p. The probability that zeta 2 is equal to 0. So here we have a branching process. So here we have the first person. So the first person can either like not infect anybody with probability 1 minus p, or it can actually infect 2 people with probability p. But now, each of these people can infect no people with probability 1 minus p, no people with probability 1 minus p, or you can actually have that one of them infects 2 people with probability p. Okay, so p of z2 equals to 0 is equal to gx of gx of 0, which in this case is going to be gx of 0 is 1 minus p. But gx, what we had seen, is 1 minus p plus p times 1 minus p squared. Okay, so the probability that you get extinct at this level is going to be the sum of the probability of getting extinct at the first level plus the probability that this guy didn't have any offsprings and this guy didn't have any offspring. Okay, so this is the probability of getting extinct at the beginning. And this is the probability of getting extinct at the second step. Okay, and then we can actually keep going, and we can get the probability of C3 is equal to 0. This is going to be gx of gx of gx of 0, which is just gx of this thing here, which is 1 minus p, plus p times 1 minus p squared. So what we are going to get, and you can actually just write it down, this is going to be 1 minus p plus p squared, plus, so it's going to be plus 1 minus p. So the point is you can actually write this down inductively. You can actually just get an explicit expression for this. This is p cubed times 1 minus p to the fourth plus 2p squared to 1 minus p cubed plus p times 1 minus p squared plus 1 minus p. So, okay, so even in this simple example like this, this is not such a nice expression to be computing. So the point is now to try to get like some idea of what you can say for general distributions, even if you don't know explicitly what the distribution is. Okay, so the idea of the last class was to try to get the limiting behavior for these distributions, just knowing some basic properties of this G. Okay, so let's now look at an example which is a bit easier to calculate. Exponentials usually are a little bit easier to deal with in these type of cases. And so let's assume that x is distributed with as a Poisson random variable with parameter lambda. So then gx of s in this case is the expectation of s to the x, which is just the sum of k equals to 0 up to infinity of s to the k, and now the distribution of Poisson lambda is going to be lambda to the k e to the minus lambda over k factorial. And what we had seen last class is that this is just equal, so you just put the s with the lambda together, and then we realize this goes outside, and we realize that this is just e to the lambda s minus 1. So now if we look at eta star, which is the solution, the smallest positive solution, the solution to s equal to e to the lambda s minus 1, we should notice that here, again, so the point is, what is the expectation of p lambda? So eta star is equal to 1 if lambda is less or equal than 1. So I'm not going to show you exactly how to do this, but it's just, I mean, the point that if lambda is less or equal than 1, this is the expectation of lambda is the expectation of x, because p0 is the x is distributed with a Poisson. So if we take expectation of x, you actually get lambda. So if lambda is less or equal than 1, then the probability of extinction is equal to 1. Now, on the other hand, if lambda is bigger than 1, then eta star is strictly less than 1. Okay, so the solution of this guy is actually strictly less than 1, and this follows from the theorem that we saw last class, or you actually try to find the solution to this, which we cannot find explicitly. Okay, what is interesting is what happens in the following case. So let's assume that lambda is positive, is bigger than 1. Then the probability of extinction is a number between 0 and 1. Okay, so the probability of extinction is non-zero, and it's actually smaller than 1 because we are under the case that this is happening. So we can start thinking what happens, what type of process we obtain if we already know the virus will go extinct. So this would be the other way around. So let's say that we look at historical data in which we look at a virus that we know, and we know that the virus eventually got extinct. And we assume that the virus was spreading with a Poisson with parameter lambda. Now, if we want to try to get this parameter lambda, but we know that it's extinct, so we actually need to put this information into the system to actually try to get what the parameter lambda is. We are not going to calculate the lambda explicitly, but let's look at what I'm trying to say. So we're going to consider x prime, which is the distribution of the infected people by patient 0, if we know the virus went extinct. So let's think of it like this. So the first person that went with Brazil to the coronavirus actually infected like 10, 20, 100 people. So let's say that the virus died off naturally, so without any control or anything. So can we actually guess how many people did the first person infect? So if we have access to its distribution, can we actually understand when the first person infects less than a certain number of people, will actually the process be likely to go extinct or not? So what we want to understand is what is the probability that x prime is equal to, let's say, k, which is equal to the probability that x is equal to k, given that we know that the virus went extinct. Okay, so if we know that the virus went extinct, okay, so what we know is this is the probability that x is equal to k intersection extinction over so eta star. So now what we can do is the sort of type of bias rule. So having the intersection of x equals to k of extinction can be the same as saying that we have here we have lambda to the k. So this would be the probability of extinction. So here, let's say, this is x00. So this is the first person. So patient 0, how many people did patient 0, so x01? So how many people did patient 01 infected, given that the virus got extinct? So now we can think of it as the intersection of how many people did patient 0. If patient 0 infected k given extinction, this is the probability that we have extinction given x0 1 is equal to k times the probability that x0 1 is equal to k over eta star. But okay, now, so what is the probability of extinction given that the first person infected k people? So now we could think, because all of these things are independent, once that, so we have the first person, and this guy has infected k people. We can think of each one of these guys as an independent, each person starts an independent Galton-Watson process with distribution x, which is Poisson lambda. So, but we actually calculated what is the probability of extinction for a Poisson lambda, and this is equal to the probability of extinction to the k, because each one is independent. So this probability here is going to be equal to eta star to the k times lambda to the k e to the minus lambda over k factorial over eta star. So one of the things is now we want to understand this distribution as a Poisson distribution itself. So eta star is a solution to eta star is equal to gx of eta star, which is equal to the exponential of lambda times eta star minus 1. So 1 over eta star is actually equal to e to the lambda of 1 minus eta star. So then this 1 over eta star here, I can actually get it to be equal to e to the lambda 1 minus eta star times eta star lambda to the k e to the minus lambda. So if we actually cancel out this one with this one, and so sorry here with the k factorial over thing, so this is distributed as a Poisson random variable with parameter eta star times lambda. So now actually what we are going to see is that if the process goes extinct, then for further generations, we can do the same argument to find that x prime, which is equal to the number of people. So in this case, x prime, before it was the number of people that the first patient infected, but this could be in general. So the number of people a patient infects is going to be distributed as a Poisson with parameter lambda eta star. So let's say that we look back in hindsight. So if we look, instead of the coronavirus, we look at SARS. So if we look at the outbreak of SARS, which went extinct naturally, we need to solve. So we need to solve this nonlinear system of trying to understand what is the, so eta star is the solution to e to the eta star times lambda minus 1, I think. Sorry, this is e to the lambda eta star minus 1. So actually, when we see the data and we try to fit it, instead of trying to fit it by a Poisson with lambda, we have to treat it with a Poisson times lambda star with eta star. With eta star is depending on lambda itself. Okay, so if we actually want to see what the infectivity really was, of the potential infectivity of this virus was, we have to actually account for this nonlinearity here. Okay, so I think this is what I wanted to say for today, and I'll give you some details of the exam in an email.